Okay, good morning, afternoon, or evening, everybody. This is your host, Jennifer Brennan, and thanks to all of you who've just joined us. I'd like to welcome you to the NASA ORNL DAAC, MODIS and VIIRS Data Tools and Services at Your Fingertips webinar. While everybody's logging in, and I know that most of you have already noticed that, we do have two optional polls at the bottom left and middle portion of your page, and I'd like to thank all of you in advance for your feedback on these polls. I've got 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. First, what I'd like to do is review just a few logistics related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. So if you have any questions or you have any issues, what I'd like for you to do is enter those into the Q&A pod, and that's located on the lower right-hand side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect catalog as well as to our NASA Earth Data YouTube channel within a couple of days of completion. And then what I'll do is I'll send an email to all of the registrants with links to the recordings, and this will include both a direct link, which will enable you to download the presentation files, as well as a YouTube recording link. Okay, and then in addition, today's presentation file will be available for download at the end of the webinar. Regarding timing, as is the case for most of our webinars, today's webinar is 1 hour long. We've allocated 45 minutes to the presentations and live demonstrations with an additional 15 minutes for the question and answer period. So once our speakers have finished with their presentations, what we'll do then is we will transition to an optional final set of polling questions. And we have a few of those today, so we'll probably give them, 4 minutes or so, and then from there we'll move directly to the Q&A period. And then just one final note, depending upon the volume of questions that we receive during the Q&A period, I will extend the Q&A period an additional 15 minutes to 3:15 p.m. Eastern Time for those of you who may wish to stay on the line. All right, during today's webinar, I'm going to go ahead and pull up the agenda at this point. We will have 2 speakers. Our first speaker is Dr. Rupesh Shrestha, who is a remote sensing scientist at the NASA Oak Ridge National Laboratory Distributed Active Archive Center, or ORNL DAAC. He will spend the first half of the webinar providing an introduction to MODIS VIIRS land product subsets and the associated tool suite. And then what he'll do is he'll transition to a live demonstration where he will showcase the user interface for the Global Subsets tool, the Fixed Sites Subset tool, and also the Web Service. And then during the second half of today's webinar, our second speaker, Jack McNeilis, who is also a remote sensing scientist at ORNL DAAC, will provide an overview to MODIS VIIRS quality filtering. And then afterward, he will transition to a use case demo with Jupyter Notebook. And today he will be using one of the Suomi NPP VIIRS Level 3 500 meter 16-day vegetation indices data product. With that, it is my pleasure to introduce our first speaker for today, Dr. Rupesh Shrestha. Rupesh?
So, hi Jennifer, thank you. Thank you for the introduction. So we'd like to welcome all to this webinar on ORNL DAAC, MODIS and VIIRS, data tools and services at your fingertips. In this webinar, we'll introduce you to the ORNL DAAC suites of tools for making the MODIS and VIIRS land products useful for the science and other user community. All the resources and the links to the webinar is available at the URL here. MODIS is on board NASA's Terra and Aqua satellites and has been collecting data since 2000, offering almost 18 years of consistently produced land product data. The VIIRS is on board the Suomi NPP satellite, a joint partnership between NASA and NOAA. The VIIRS provide continuity to the MODIS mission by extending and improving upon the MODIS measurements. The recently released VIIRS land products use similar algorithm to the MODIS products and are produced in the same graded system and temporal frequencies. More information about these products are available at the following websites. The ORNL DAAC is one of the NASA's distributed active archive centers. It is operated by Oak Ridge National Laboratory, Environmental Sciences Division. The ORNL DAAC is a primary archive for terrestrial ecology and biogeochemistry datasets. It also archives and distributes various in situ, modeling, and remote sensing data from the NASA field campaigns. Because of the complexity and the size of the MODIS land products, there was a need for a tool that allowed retrieval of the MODIS data in an easy-to-use format, especially for the land science community. The ORNL DAAC developed the subsetting and visualization tool more than 10 years ago now to meet the need. The tool has been continually expanded and developed since then and has been quite popular among the community. Among other changes, we recently added VIIRS land products, released a new web service, and a new tool to access pre-processed cutouts. The ORNL DAAC, MODIS, and VIIRS tools primarily consist of 3 tool sets. All the tools are available at this web URL at the bottom of this presentation. The first is the global subset tools to create the subset for user-defined locations and extend. This relies on email delivery of the order, and there is usually a wait period between the order submission and the order delivery. The second tool, called the fixed site subset tools, include a pre-processed cutouts for more than 2,000 sites. This includes several flux tower sites, USCRN sites, Aeronet sites, and other network sites. Because all the subsets are pre-processed, there is no wait period and the data can be retrieved instantly. The third tool is a web service, a standard-based application interface for downloading the data programmatically. The web service is particularly useful for the users requesting the data over larger areas. We'll go over each of these 3 tools in the following demonstration. Let's first look at the global subset tools. A user needs to be logged in using NASA's Earth data login before an order can be submitted. If this is the first time you are using the NASA's Earth data system, a new account can be created by clicking the register button here. The Earth data login provides a simple, centralized mechanism for user registration and user profile management for all users accessing data. The information provided by users when they register helps NASA better understand how the data are being used and the diverse needs of multiple user communities. Let us log in here. Once logged in, the user will first select a location of interest. This can be done either by entering the location in the text box here or by moving the marker on the map. Once the location is selected, let's click the continue button. In this page, the user can then select MODIS or VIIRS products. Currently, there are 4 VIIRS and 18 MODIS collection 6 land products available. We plan to add more VIIRS and MODIS products in the coming months. We also plan to add other related products useful to the land science community. For example, among others, we will also be adding DayMate data, which provides the gridded estimates of daily weather parameters for North America. Please watch this space for the future updates. Now, in the search box here, let's find all the leaf area index or LAI products. There are currently 5 LAI products available. Let's select VIIRS VNP15A2H. This product provides LAI and fraction of photosynthetically active radiation or FBAR at 500 meter resolution at 8-day interval. In the space below, the user can enter the size of the grid. The default is 3 km above and below and 3 km left and right of the point of interest. This will produce a subset of about 6 by 6 km. The user can enter a maximum of 100 km. Let's leave it at the default and click continue. Now, select the starting and the ending date. The order will also create a GeoTIFF file for the subset. The default projection system for the GeoTIFF files is in the native MODIS sinusoidal projection system, but it can also be reprojected to the geographic projection system. Let's leave it at default and let's review the order. If everything looks okay here, we can now submit the order. Upon submission, you'll get a unique ID for your order. And you can track your current and previous order at the order history page. The order history page allows you to manage your orders, bookmark them, and rename them. There is also a map showing the locations of your orders so that you can find your orders easily. Once an order is processed, you'll get an email. The email will also include the suggested citations to include in a manuscript publication that uses the subset data. Clicking on the Access Order link will take you to the order delivery page. This is an example order delivery page. This page can be shared with your collaborators, students, and others, and they don't need to log in to view the visualization or download the data. The order delivery page includes different sections. At the top is the download section, where you can download the raw data, quality filtered and scale data, and the statistics data. The table here lists the data only for the science band. Other data bands, statistics, phenology, land cover, can be accessed by clicking on the CSV data link at the top here. Now let's go back to the order page. In the table, the right column lists the data files with a land cover mask applied, meaning that the pixels different from the land cover to that of the subset center are maxed out. This section also has citation and the quality control details at the QC details tab. Recommended quality control criteria that was applied by default are shown here in the table. They are labeled as presented and suppressed. If you scroll down, the next section is the time series visualization. The blue lines are the central pixels, and the red lines represent the average of your subset area. You can stack by year if you are interested in comparing between the years. You can also visualize with land cover filter applied. If you scroll down more, you can visualize the subset grids by clicking this green button here. First, select the date you want to visualize, and then when you click the button, this page shows the raw and quality filter image for the date. The filtered pixels in the second columns are shown in white color. Now, let's go back to the order delivery page again. And at the bottom, the section called Additional Information provides land cover, phenology, and R codes and graphics. Now that we have looked at the global subset tool, let's go back to the Get Data page again and look at the second tool, the Fixed Site Subset tool. The tool includes pre-processed cutouts of about 8 km by 8 km area for the field and flux tower sites. These fixed sites data are available instantly through the web interface and the web service or API. You can access the site page either by searching in the bar here at the top or clicking on one of the green dots on the map. You can also list all the sites by clicking on the list button here at the top. Now, let's search for a site called Tangier Ranch. This is one of the Ameriflux sites in the foothills of Sierra Nevada in California, USA. In the table below, if you click on any of the product links, it will take you to the product page for the site. So this page is very similar to the Global Tools order page. The first section is the download section. Let's download a CSV raw data band here. You'll need to be logged in to download a file. And let's open that file. The first few columns are information about files, products, and dates, but the real data starts from the 6th column onwards. The sixth column is the upper left pixel, and the last column in that row is the lower right pixel of the subset. The number of data columns is dependent on the spatial resolution of the product. Now if you go back to the product page, there is a button called Pixel Numbering Scheme. It will show you how the pixels are ordered in the CSV file. The center pixel is marked blue here. Now, let's also go back and download a statistics JSON file and open it. So this file gives you various statistics for the subset. You can also retrieve a center value here if you want to. Now let's go back to the product page and scroll down. Now here you can visualize the grid interactively, look at the values of each pixel, or navigate through the time slider. If you go back to the top of the page and click Subset Summary, you'll notice that we have assigned each site a unique site ID. But if you are a user of a network such as FluxNet, Neon, or others, you can also access this page using the ID of the network itself. So if you go back to the main fixed site subset tools, in the documentation page, it is shown there. The FluxNet ID of this Tangier site is US-TON. So if a user specifies the network name and the network site ID, the page or product can be directly accessed from these URLs shown here. All of these data are also available from the web service by submitting a GET request like shown in the third section, third bullet here. Now let's go back to the GET data page again and look at the third tool, the web service for retrieving the data programmatically. We recently migrated the web service from an older SOAP-based API to this new REST-based API, which uses a much simpler protocol and allows data access using standard HTTP methods. The web service can be used to request data for a user-defined subset area, the capabilities of which are listed in the top section of the table here. The data from the fixed size tool can also be requested using the API. This is listed in the bottom section here. I want to quickly point you to the API user interface here. This interface will let you familiarize yourself with the various capabilities of the web service. So of the three tools we just discussed, the global subset tools and the fixed size subset tools provide quality filter and scale data in addition to the raw unfiltered data. But with the web service, user can only retrieve the raw data and then will need to apply the quality filter on their own. In the next section of this webinar, Jack will demonstrate how to retrieve subset data using the API and more importantly show you how to apply quality filtering exactly the way you want. I will now pass it to Jack for his part of the webinar. Thank you.
I'm going to follow Rupesh's introduction to the tools with examples for a few web service functions and also how to apply the custom quality criteria for filtering data accessed using the web service. But first I want to give a quick introduction to the MODIS and VIIRS quality layers in case we have new users listening in. For the demo, we're going to be working with the Enhanced Vegetation Index data from the VIIRS Vegetation Indices product. And I'll refer to the Enhanced Vegetation Index as EVI from now on. EVI is good for getting a general sense of the productivity and condition of the vegetation with greater sensitivity to canopy structure compared to other broadband vegetation indices like NDVI. It's used across a variety of scientific disciplines for monitoring seasonal vegetation dynamics and has been a core product generated for both the MODIS instruments and more recently for VIIRS. VIIRS Vegetation Indices has the product code VNP13A1. Here's the list of sub-data sets included in the VIIRS VI product. This table can be found in the user guide for VNP13. The 3 rows in green are the primary data layers that are plotted for you on the order delivery page when you place a global tool order for the VIIRS Vegetation Indices product. They are EVI1 and 2 and NDVI. Below that, the row highlighted in yellow is the quality layer. I'll call it the QC layer from now on. At least one QC layer is included with every MODIS and VIIRS data product, and they're important because they inform us about the reliability of the data on a pixel-by-pixel basis. Hopefully these raster grids can help you get a better idea of what the QC layer is used for. Here, each row of grids represents a day of EVI observations over a 5 by 5 kilometer area, along with the corresponding QC layer in the middle and the resulting EVI grid with poor quality data masked out on the right. The white areas in the third column of grids are where pixels have been filtered out of the data. You can see the white space in the second row of filtered EVI matches up with the tan-colored area in the QC layer for that date. And if you look really hard at the QC layers in the first and third rows, you might see the dark purple area corresponding to filtered pixels for those dates. You can see that every observation gets its own quality assessment, so there's a one-to-one match between the number of observations in the data layer and the number of values in the QC layer. In the case of the VI products, the values in the QC layer are 16-bit integers, and they store a variety of information about the quality of the observations in the EVI layers. The QC layer for VNP 13A1 is named 500 meters 16 days VI quality. The quality information stored in this layer is broken down into 9 bit groupings, representing the 9 different quality flags listed here on the slide. The table on the right is the key to extracting information about the data quality from each of the quality flags. This is an important table, so remember to check the user guide for it. There's a link to the user guide in the Jupyter notebook. So here we'll take a stab at understanding the bits using a QC value of 2185 as an example. The binary representation of that number is the string of zeros and ones that you see on the right above the table. You can split that string into each of the 9 bit groupings, and counting bits from right to left, reference that important table from the user guide to determine what each flag is trying to tell you about the quality of the corresponding observation in the EVI layer. Looking at the table in the bottom right, you'll see the quality description for each of the flags stored within that value of 2185. The pair of bits for the first flag indicates that an observation was recorded, but that you should have a closer look at the other quality flags. The second set of bits are for the VI usefulness flag. In this case, it's telling us that the pixel is of decent quality. The third flag indicates that the aerosol quantity was average during this observation, and so on. This should make more sense to you when you see them in action in the demo. Now, before we get to the Jupyter notebook, I want to point out again that the MODIS VIIRS global tool applies some quality filtering that's understood within the research community to be a good general baseline for all users to consider when using MODIS and VIIRS data. As Rupesh mentioned, some details about the filtering applied by the global tool are shown on the QC Details tab of the Order Delivery page. Remember that CSV files labeled Filtered and Scaled have the filtering applied as well as the product scale factor, and you can download those on the Download Data tab. But there may be situations where the filtering applied by the global tool doesn't meet your needs, so let's go to the Jupyter notebooks now, and I'll show you how to do the quality filtering yourself. As I mentioned, we're going to do this demo in R, but the same methods are easily applied in Python or any other scripting language thanks to the flexibility of the REST API. There's a Python version of this notebook on the ORNL DAAC GitHub page if you prefer to follow along that way. It's a little bit shorter, but has all of the core workflow content. So first we're going to work through examples for using 2 functions of the web service, the dates and subset functions. Then we'll use them to get some EVI data to do the quality filtering. The goal is to go from this plot that assumes all data in the time series are valid to this plot below by removing data that doesn't meet our set of quality criteria. And we'll do that using a masking method that looks something like what you see in this table and the 3 raster grids below. Then we'll use the same masking method to plot the time series by land cover class from the MODIS land cover product, MCD12Q1. The basic requirement is a package for submitting GET requests. We'll use HTTR in this example, and that's really all you need to interact with the web service. The equivalent package in Python is called requests. It also helps to have a package for converting the web service response into a familiar data structure. We're going to use JSON-Lite to convert a JSON response to a data frame. If you choose to request the data in text format instead, you could use the reader package to parse the response. So now we can go ahead and load our required packages. We'll also load ggplot2, scales, and VIIRS for help plotting, and raster and rasterviz for gridding the data. Now we'll use the products function to test our connection to the web service. Here we set the URL endpoint that we'll use to access the API, and then submit a test request to the products function. A 200 status means that we got a response. We can go ahead and use HTTR's content method to parse that response. It conveniently parses to a list by default. And within that list is another list for each product that gives you some details about them. So here we've printed only the first product in the list, which is the land cover from MODIS MCD12Q1. You can see it's generated once per year at 500 meter resolution. And now you know how to send a request to the web service. So let's see examples for the dates and subsets functions. We're going to use them to submit a request for the full available time series of EVI data from VIIRS for a site in the Great Smoky Mountains National Park near Gatlinburg, Tennessee, and then we'll use that data throughout the rest of the demo. There was a large fire at our site in late November and early December 2016 that burned up a lot of the area, so we should be able to see the effects of that fire on local vegetation in our EVI time series. The dates function returns a list of available dates for any MODIS or VIIRS land product at any lat-long coordinate. You provide the product and the coordinate inside the URL string, and you get back 2 lists of dates, the MODIS date and the calendar date. The MODIS date is a string with A followed by the year and the day of the year. And we'll use the MODIS date string to specify the time bounds for our subset request later on. The dates function is important because there's a 10-file limit per subset request. That limit is in place to prevent connections from timing out if there's a request for data over a large area. So we'll need to iterate through our list of dates in increments of 10 or fewer. So in this next block, we're going to set the lat and long and product parameters that we'll use for the remainder of the demo, and go ahead and request a list of dates for VNP13A1 at our site. What we've done is split the response into vectors of MODIS and calendar dates and printed the first 10 MODIS dates, and that's what you see right here below the code block. And now you know how to use the dates function, so we will try out the subset function, which lets you retrieve a spatial subset of any MODIS or VIIRS land product. You specify a product, the latitude and longitude of the subset center, the band name, which you can get using the bands function, and the start and end MODIS dates, and also the subset window, which you set using the number of kilometers above and below and left and right of the subset center, just like you do with the global tool. The response contains a bunch of helpful information about your subset that can be used to grid the data. It also has the scale factor, which you'll need to convert the data from integers to floats. And the actual EVI data that we're interested in is contained in the subset element of the response, which we'll see here in just a minute. In this next code block, we are going to run the subset function for the first date in the list that we just made above. At the top are the rest of the subset parameters that we'll use for the remainder of the demo. And below that is a simple function that combines all of the parameters into a URL string that we'll use to submit the request. We're going to request a roughly 5 by 5 kilometer area around our subset center. So run that, and here is all of the subset metadata that I told you about before. And below that are the contents of the subset element. It's parsed to a data frame by default with columns for the MODIS and calendar dates, the band name, the tile identifier, and processing date. And the last column, the data column, has an array of values that cover our subset area. In a minute, we're going to reformat this into a more useful structure for plotting. Down below in this next code block, we're going to save some of the subset metadata to use later. We'll keep the number of rows and columns, the lower left corner coordinate in sinusoidal meters, the pixel size, and the scale factor for EVI. And we'll print some of those too. So the next code block shows us how to convert the subset that we just requested into a format that matches the CSV outputs from the global tool. If you take just the data column from above and transpose it, you get a data frame where each row is a time step and each column is a pixel. Of course, we only have one row because we only requested the first date of our list, but because we formatted our data this way, you can use any of the workflow from here forward on CSV data from the global tool as well. Now in this next code block, we define another function called rTemplate that creates a raster object from our subset metadata. This is why we saved all of those metadata parameters above. We just plug in the number of columns and rows, the lower left coordinate of the subset, and the cell size, and we get back a raster object that we can use to visualize the subset. You can also save the raster object as a geotiff using the two commented lines at the bottom of this code block. So make a raster object for the subset that we just got and reproject to WGS84 and run it, and we get these two nice plots of our test subset right here that you can see. So now we know how to use the subset function, so we can make a time series of EVI data. Remember, because of the tile limit, we have to iterate through our list of dates and submit a request for each one. This is the code that you use to do that. But we ran it beforehand because it takes several minutes. So we're just going to load the data from a file. And now we already have something that we can plot. This code block is basically just getting the mean and standard deviation across the whole subset area through time and plotting with ggplot. Our time series spans from the first available VIIRS dates in January 2012 to the most recently processed date in 2018. Remember, the fire happened in November and December 2016, and you can definitely see a difference during late 2016, even though EVI is at the lower bounds of the seasonal cycle. But the more noticeable difference is in the peak greenness of the following spring and summer in 2017. It looks like we can see the beginning of a recovery this year and what data we have for 2018 as well. But we're obligated as good remote sensing scientists to evaluate the quality of the data in this plot, and we'll learn how to do that by making a table that looks like this. This table should help us to understand the meaning of each of the values in the QC layer so we can decide what filtering criteria to apply to our EVI time series. Down here below is the quality flag table for the vegetation indices product again for your reference, but we'll move past that for now and go ahead in this block start by creating two new data frames for each of the EVI and QC layer time series. And we'll also get a list of unique values within the QC layers and print those below. So here are all of the unique values from the QC layer, and below that are the first 5 rows of our EVI and QC layer time series. Now we'll make a table that describes the quality flag information stored within each of those unique values. Remember, there are 16-bit integers for the vegetation indices product. So in this next code block, we're making an empty data frame with a row for each one of those values, a column for each bit, so 16 columns, and another set of columns for each of the quality flags in that table above from the user guide, so 9 more columns. We run that and we see the first 5 rows of the empty table. Keep in mind that you don't need to make this whole table. If you know which flags are relevant to your analysis, you can just make the table for only those flags. But we'll go ahead and fill out the whole thing in this case. The next step is to loop through each row to get the binary representation of each integer value and populate the 16-bit columns with a 0 or a 1. Then all the lines below that are rules for populating the quality flag columns based on the combination of bits in the column that we just filled a second ago. So it helps, but it's not entirely necessary to know what's happening in this big code block. You can just plug this into our workflow and use the table in the same way that we will in the next steps. So run that and see here are the first 5 rows of the completed QC table. Now, if you're working outside of the Jupyter notebook, you can sort by the different columns to see if there are any flags that jump out at you as pixels that you might not want to include in your analysis. Remember to check the user guide to get a better idea of what each quality flag means. But we're going to filter our time series using some criteria that I've listed right below. The goal is to remove rows from our table that pass our quality criteria so that we can use the remaining integer values to mask our time series of EVI. The criteria that we're using are, we'll remove pixels with a Modeland QA flag that indicates that a pixel was produced but was most probably cloudy, or that the pixel wasn't produced due to reasons other than clouds. Also, we'll exclude pixels with a VI usefulness flag indicating quality of level 4 or worse. Also, aerosol quantity must not be high. Adjacent cloud detected must not be yes, and possible shadow must not be yes. So we run that, and here are the first 10 rows of our final QC table. All the values that remain in the leftmost column called integer value represent values for pixels that we do not want and that don't meet our quality standards, and we'll remove those pixels in the next code block. So now we can filter the EVI data. Down below, we are looping through the time series. Remember our data format where rows are time steps and columns are pixels. And for each time step, we index the columns with QC values that are still in that leftmost column of our final QC table. Then we mask those same indexed columns from the EVI time series and do that for every step. And now we have a filtered EVI time series, so we can go ahead and plot it again. We'll get the mean and standard deviation throughout the time series, and this time we'll also add columns for the year and day of the year and make 3 plots with ggplot. The first plot now has blue bars that show you the percentage of pixels that passed our quality criteria at each time step, as does the second plot, which is just zoomed in on the period surrounding our fire event towards the end of 2016. By and large, our data is consistently good quality, but that's definitely not always the case, so it's important to go through this process. Sometimes you'll find data values that look reasonable, but when you check the quality layer, they're consistently marked as poor quality, and that can happen for several months out of the year, every year in certain areas, like those with a rainy season, for example. So it's important that you go through this step when you're using the MODIS or VIIRS data. The last plot is a time series stacked by year, and the main takeaway from this plot is just that the bright green and yellow EVI curves for 2017 and 2018 are well below the ones for the preceding years. Here in this next code block, we'll quickly learn how to make the figure from the slides that shows us the QC filtering workflow. We're using the rasterviz function level plot to make these nice grids. And this is just for a date in late June 2012 that I picked because it has about 50% good data. So take a closer look at this code in the Jupyter Notebook if this interests you. And now we'll go to the land cover filtering example. Again, the global tool already does this for you, but sometimes your analysis may require you to use some other classification scheme or to group land cover types into categories like grazable and non-grazable land, for example, or any other number of things. So we're going to learn how to do that here. We requested type 1 land cover from MCD 12Q1, which is the classification scheme used by the International Geosphere Biosphere Program. And there are several other land cover classification schemes in MCD 12Q1. So check out the user guide to see which one is best for your use case. We're going to load the data for 2016 from a file again, but you can see right above here is the code to submit the subset request for that data. We use the same functions as we used above. And in the next block, we're making a table with the classification scheme for your reference. And finally, below that, we are looping through each time step and calculating the mean of all the pixels for each land cover type using the same indexing method as we used to do the QC filtering above, then saving the results as a new data frame. So here are the first 5 rows of results. As you can see, there are only 3 land cover types represented because we've got a pretty small area that we requested, but we can go ahead in the next step. We're ready to plot the data again and see the result by land cover type. So you can see the same trend as we observed in the previous plots. In all the years through 2016, EVI peaked higher for deciduous broadleaf forests than for the other 2 land cover types, urban area and woody savannas. Then the difference between the classes wasn't as striking in the spring and summer of 2017 after the fire. And that's pretty much all we have for you here in the Jupyter Notebook. If you scroll down below, though, you can see we've included the code to generate the QC tables for land surface temperature and leaf area index products, and I'll get around to adding the other products sometime soon. You can see all the Jupyter Notebook content on the ORNL DAAC resources page and also our GitHub page. The workflow, again, is also on there in Python. And you can find some more details about each of the web service functions that we didn't go over here at the ORNL DAAC MODIS VIIRS webpage. Thanks for listening.
Okay, well, thanks very much. Thanks very much, Jack. And at this point, what we'll do is we'll transition to a final set of polling questions. And, you know, once we get to the Q&A, we'll give these about 4 minutes. Once we get to the Q&A, I will want for you to provide the URL to where they can access the code. If you guys want to type that into the notes pod for me, I'll enter it in during the Q&A for everybody. And I can also include that in the follow-up message to our registrants. We really appreciate your feedback on these polling questions, everybody. Thank you so much because, especially with respect to future webinar topics and future data sets, I know that the Oak Ridge DAAC finds that very useful input in determining their future webinar topics with our team. So thanks again. We're going to give this about another minute or so since we do have a couple of short answer questions. I want people to have an opportunity to, jot down some ideas. But certainly if you think of something once the webinar, has completed, feel free to either jot them into the Q&A pod, or you can certainly email me, and I will forward those messages along to our speakers today. All right, so let's give this just another minute or so, and then we'll move directly to the Q&A. We do have a couple of questions that were asked a bit earlier, and don't worry, it's a persistent feature, so once we transition, those questions will still be there. All right, so another minute or so, and then we'll carry on with the Q&A. Okay, well, thanks everybody. At this point, let's go ahead and transition to the Q&A session. And just really quickly, a couple of points. The first one is that we do have probably close to 90 data discovery and access webinars available on our YouTube channel. These webinars are, basically we hold these in conjunction with scientists and user services representatives at all 12 of our NASA Earth Science DAACs. And so you might find something that you didn't hear about today within one of those webinars. And then the second point I wanted to make is that today's presentation file is available for download in the lower right-hand corner of your screen. You'll find it in the Share pod. If you highlight the file, you'll be prompted with an option to download the file. With that, let's go ahead and pull up our first question, which was asked a little bit ago. And if you'll bear with me while I identify the question here. All right. Let's see. Okay. All right. So Jack and Rupesh, the first question is, regarding the web services, is there any plan from NASA or USGS to deliver a cloud platform such as Google Earth Engine for NASA data?
Hi, this is Allison Boyer from the ORNL DAAC, and I can answer that question. NASA is exploring options for cloud computing resources for scientists, but there are no specific services available at this time. However, a lot of the MODIS data and other products are available on Google Earth Engine. So we encourage you to check that out and see if it meets your needs.
Okay, thank you, Allison. Let me pull up our second question here. Give me just 1 second here. Okay, here, trying to, okay, so the next question is, okay, thank you, one question if I may. How accurate is the data for very small subsets, for example, NDVI for 1 by 1 kilometer or even 0.25 by 0.25 kilometers?
So those data are accurate as the MODIS data itself. So if you, so there is no less accuracy when you just order 1 pixel or if you order more pixel. So it does not depend on the size of the subset you want to order. So it will be as accurate as the MODIS data can be. Thank you.
Okay, thank you, Rupesh. So moving to our next question, and so this was kind of covered a little bit earlier. You mentioned the question was whether or not the R code is available on the site, and Jack, you mentioned that it was available by accessing both on GitHub and then further linked to the Oak Ridge DAAC resources tab, correct?
Yes, we have a resources page on the ORNL DAAC website that you can then link to our GitHub page to get the Jupyter notebooks that we went through in the webinar. There's both an R notebook and a Python notebook, and there's also a bunch of other webinar content on our resources page not related to what we just went over today. You might also be able to download it through one of the links here on the Adobe Connect. I'm not sure about that.
Okay, great. Thank you, Jack. So the next question is, using the notebooks, is there an easy way to visualize the pixel boundaries for the data over some satellite imagery for the site? Or is it possible to save shape files with the pixel boundaries or save the bounding coordinates for the pixels? And if you need me to repeat that question, let me know.
Yes, repeat that if you don't mind, Jennifer.
Sure. So the first part of the question is, using the notebooks, is there an easy way to visualize the pixel boundaries for the data over some satellite imagery for the site? Or is it possible to save shape files with the pixel boundaries? And then finally, or save the bounding coordinates for the pixels? So is there an easy way to visualize the pixel boundaries for the data over satellite imagery for the site? Or is it possible to save the shape files with the pixel boundaries, or is it or save the bounding coordinates for the pixel?
So, I'm not aware of any way to change our pixel grid into a shapefile in R. I'm sure that you could come up with some workflow to do that, but you can overlay the subsets that you request from the web service on top of a satellite map to see if you've covered your study area. I think there's a good package called a Mapbox that'll let you do that. I'm sure there are other packages that you could load to help you do that as well, but you're just going to have to do some Googling, I suppose. I hope that answered your question.
Okay, and if not, perhaps this is something we can also follow up more in depth offline as well. And then the next question is this working only for the Oak Ridge DAAC? I assume this is referring to the services and the tool suite that was referenced today. You're referring to whether or not it's working for only Oak Ridge DAAC data holdings?
Currently, only MODIS and VIIRS data products, MODIS and VIIRS land data products are available through the web service and the other tools and services that we demoed today. But in the future, as Rupesh mentioned, we're going to be adding some other products supported by the ORNL DAAC like DAMET, and we're looking into what other products are good for the capabilities of our services as well.
I would add to that that there are other DAACs that have other data products, and there are other subsetting tools. For example, there's the VIIRS subsetting tool, which allows you to access MODIS products and other data products at the LP Land Processes DAAC. So if you're interested in other remote sensing products, I recommend you check out some of the other DAACs for subsetting capabilities.
Okay, and related to that, I've just included the URL to the LP DAAC website. The tool is a point-based data extraction tool, and it's called VIIRS, and so I've included the link there, and you should be able to find that by accessing their tools section within the website. And then the next question here is, how is the searching scripting we saw related to CMR searches on Earth data?
Not at all, I think. I mean, so what we were seeing in the Jupyter notebook was querying the data pool of MODIS and VIIRS land product data that we keep on site here at the ORNL DAAC. So any data that's accessed through the web service is just interacting with our backend to retrieve subsets from those files that we have here in-house. You can go to the ORNL DAAC website or the Earth Data website to search the CMR records for other data products if you need to do that.
Okay, thank you, Jack. And the next question, I don't think it's available through your subsetting tool suite, but maybe they are. So the next question is, are daily VIIRS nighttime lights products available? Where can I download them? So I can answer the where you can download them if they're not available within your subsetting tool suite.
So they are not available at ORNL DAAC. So maybe, Jennifer, if you share them where they are.
Yeah, so there are two, and I can also follow up offline with this particular user. So one way that you can visualize the data and also download the underlying granules, although they are not subset, is by accessing our Worldview application. So that's the VIIRS day-night band, and I can follow up on email. Then I believe also you can go through the search.earthdata.nasa.gov. So what I'll do is I'll follow up separately with this participant regarding this data query. But those are two ways that you would be able to access this data. And then you're welcome we will be, as I mentioned earlier, we're recording the webinar, so if you missed something during the demo, certainly you could take a look at this a bit later. Are there any additional questions at this time? Okay, well, I'll give it a couple minutes or so. If there are no further questions, what we'll do at this point is we'll log off from the audio component of the webinar. And then I typically leave the virtual meeting space open, like 10 minutes or so, in case anybody thinks of a question or would like to follow up on something. You can jot that down into the Q&A pod, and I will send the log along to our speakers. So if there are no further questions, I would like to thank all of you. Okay, there is a question. All right, so what are the differences between column I'm not sure if you're referring to the data versions, column V5 and column V6. Do I have that right? Collection, yes, V5 and V6.
So the collection 5 is not available anymore. So that has been replaced by collection 6. So collection 5 is retired from all of the of our holding, and it has also been retired from LP DAAC holding. So you would have to contact MODAPS if you want to get the collection 5 reprocessed or something. Yeah.
And this is an additional question where we can certainly follow up offline, point you to some documentation that actually spells out the differences between the two versions, and further I can, get you in contact with the DAAC here at Goddard that might be able to provide you access to the V5. So I will follow up separately offline with this user. All right, are there any additional questions? Okay, well, if there are no further questions, thanks to our speakers today and also to Dr. Alison Boyer for joining in for the Q&A portion of the webinar. Thanks to all of you for taking some time out of your day to join us for the webinar. Right, how do we explain the differences between them? I think that you'll find, so the data get reprocessed, right? And if you guys can correct me if I'm not accurate on this, algorithms are improved. The data quality is improved with the new versions, but there are specific changes that are made between version 5 and version 6 data products, and really that would be true for any new version for any data product. And generally, the data documentation, which I will provide a link to, will really lay out the specific differences between the two versions. I would not know off the top of my head unless one of you would know the specific differences between V5 and V6. Does anybody have an answer to that?
Jennifer, I think that your answer was perfectly adequate. There were algorithm updates between the two collections, and all of those would be documented in the algorithm theoretical basis document that's provided with each MODIS product. You can find those at the product page on LPDAAC's website. You're going to have to look to that too.
Yep. So Guillermo, what I'll do is I'll follow up with an email and get you started in the right direction. And then certainly if you don't find all the answers you need, you may always submit a help ticket to support at earthdata.nasa.gov. But I really feel like the documentation will answer your questions. All right. Are there any additional questions at this time? Let me scroll down, and sure, you're very welcome, of course. Anybody have any additional questions? All right, well, thanks, everybody. We actually do have another webinar coming up in September. That'll be on, let me just check my calendar, on September 26th. And our Land Processes Distributed Active Archive Center will also be conducting a webinar that addresses, I think, both MODIS and VIIRS data products as well, and some of the tools that are specific to their DAAC. So if you are interested, you could sign up to receive updates for upcoming webinar by going to the tinyurl.com Earth Data Webinar. And yeah, you'll just receive mail when we have a new webinar coming out. It's usually a different discipline or suite of different data products or tools each month. Okay, well, thank you, everybody. Thanks for joining us, and thanks to our speakers. So at this point, we will log off from the audio component, and I'll leave the virtual meeting space open. All right, thanks, everybody. All right, bye-bye now.